Your app feels sluggish. Pages load slowly. Data takes forever to appear. And let's be real, we've all been there, hammering the refresh button, blaming the Wi-Fi, or maybe even our coding skills. We assume the problem is always in our front-end code or a poorly optimized API call. But what if I told you the real bottleneck, the hidden slowdown, is often lurking much deeper? Right at the very core of your application, the database. Many developers overlook this critical piece. What if there was a powerful, ancient technique, used in databases for decades, that could transform a snail-paced query into an instant response? A secret weapon that's absolutely essential for any app that needs to scale and perform? Today, we're unlocking that secret. We're talking about database indexes, and how they truly make your applications fly. Let's start with a classic real-world scenario. Imagine you're trying to find a specific name, say Sarah Johnson, in a giant, old-school phone book. But this isn't just any phone book. This one has millions of entries, and here's the kicker, it's completely unorganized. No alphabetical order. Just names, thrown in there randomly. How would you find Sarah? You'd have to start at the very beginning. Page 1, Entry 1. Then Entry 2. You'd meticulously flip through every single page, examining every single entry, until you hopefully stumbled upon Sarah Johnson. That's what we call a full table scan in the database world. Every time your application needs to fetch data without any help, the database acts like you, blindly flipping through those pages. It has to scan row by row, from top to bottom, until it finds what it's looking for. For small amounts of data, it's fast enough. But as your data grows to hundreds of thousands, millions, or even billions of rows, a full table scan becomes a monumental waste of time and resources. And that, right there, is where your app starts to feel slow. Now, let's take that unorganized phone book. What's the obvious solution? We organize it alphabetically, right? Or better yet, we create a separate, smaller book that just lists names and the page number where you can find their full details. That's essentially what a database index is. Think of it like a library's card catalog. You don't scour every single bookshelf to find a book. Instead, you go to the catalog, which is a highly organized system. You quickly find the book's title, and it tells you exactly where on which shelf to go. That's lightning fast. A database index is a special lookup table that the search engine can use to speed up data retrieval. It's a separate data structure, usually much smaller than the main data, that stores a copy of one or more columns from a table, along with a pointer to the location of the actual data row. The most common type of index structure is called a B-tree, short for balance tree. Don't worry about the complex name, just know it means it's super efficient at finding things quickly because it keeps the data sorted and structured for rapid searching. Instead of scanning millions of rows, the database can use the index to jump directly to the handful of rows it needs. Alright, so we know what an index is conceptually. But just like there are different types of roads, there are different types of indexes. The two main ones we need to understand are clustered and non-clustered indexes. And this is where it gets really interesting. Imagine our library again. A clustered index is like deciding to physically organize the entire library by author's last name. The actual books on the shelves are sorted. When you find a book in the catalog, you walk right to that spot, and because everything is already organized there, it's super efficient. There can only be one way to physically sort the books, right? So, a table can only have one clustered index. This is usually on the primary key, and it's incredibly fast when you're fetching whole rows of data because the data itself is already where it should be. Now, a non-clustered index is like having those separate card catalogs we talked about earlier. One catalog for titles, another for subjects, maybe another for publication year. Each catalog is sorted, but the books on the shelves themselves aren't necessarily ordered by title or subject. Each card in the catalog points you to the physical location of the book. You can have many non-clustered indexes for a single table, because they're just pointers. They are great for quickly finding specific pieces of information, like an email address, without needing to sort the whole dataset. So, we have these powerful tools. When do we actually use them? It's not about indexing everything, that's actually a bad idea, which we'll get to. It's about being strategic. First, if you're constantly filtering your data with where clauses, that's a prime candidate. If you're always searching for users by their email or orders by their customer_ID, an index on those columns will be a game changer. It's like having a dedicated express lane for those specific searches. Second, think about join operations. When you combine data from two or more tables, the database often needs to match rows between them. Indexes on the columns used in join conditions, like user_ID in both your users and orders table, dramatically speed up those complex data merges. Third, if you're frequently ordered by specific columns, say sorting products by price or comments by timestamp, an index can pre-sort that data, so the database doesn't have to do it every single time. It's like having all your music already alphabetized by artist. Finally, consider high cardinality columns. These are columns with many unique values, like an email address or a username. Indexing these makes sense because the index can quickly narrow down the search space. Columns with low cardinality, like a gender field with only 2 values, usually don't benefit as much from indexing because the database might still end up scanning a large portion of the data. And for even more speed, we can create covering indexes that include all the columns a specific query needs, so the database doesn't even have to touch the main data table. It can get all its information directly from the index. Okay, so indexes sound like pure magic, right? Free speed for everyone. Well, not so fast. There's a catch, and it's an important one. Just like building extra lanes on a highway speeds up traffic, those lanes aren't free to build or maintain. Indexes come with a cost. The first cost is storage. Every index is a separate copy of some of your data, plus those pointers. So, it takes up extra disk space. A table of 1 gigabyte could easily have hundreds of megabytes, or even gigabytes, dedicated just to its indexes. While storage is cheap, it's still something to consider, especially at massive scales. The second, and often more critical, cost is performance during write operations. Think about it, every time you insert a new row, update an existing one, or delete a row, the database doesn't just have to modify the main table. It also has to update all the indexes that involve those columns. This takes extra time and processing power. It's like adding a new house to a neighborhood. You don't just build the house, you also have to update the phone book, the post office records, and the local census. So, while indexes make reads blazing fast, they can slow down writes. The trick is finding the right balance. You want enough indexes to speed up your most critical and frequent read queries, but not so many that your write operations crawl to a halt. It's a delicate dance, but a necessary one for building truly performant applications. Time, 500 milliseconds, example. Create a non-clustered index on the email column. Create index IDX_users_email on users, email. Query after index, same query, but now faster. Select user_ID, username from users where email equals alice@example.com. Time, 10 milliseconds, example. So, how does this actually look in practice? Let's take a quick peek at a simple SQL example. Imagine we have a users table with millions of entries, and we frequently need to find a user based on their email address. Without an index, that select query could take hundreds of milliseconds, or even several seconds, as the database performs a full table scan SQL. Select user_ID, username from users where email equals alice@example.com. Now, let's create a non-clustered index on that email column. Just a single line of SQL. SQL. Create index IDX_users_email on users, email. After creating this index, when we run the exact same query again, the database suddenly knows how to find that email address almost instantly. What took 500 milliseconds before, might now take 10 milliseconds. That's a 50 times speed improvement, just from one small change. This kind of improvement is the difference between an app that feels snappy and responsive, and one that feels frustratingly slow. Tools like Explain Analyze in PostgreSQL or Explain in MySQL let us actually see how the database is processing queries, showing us if it's using an index or doing a full table scan. This feedback loop is crucial for optimization. On a related note, the Go standard library is getting a UUID package soon, and for those using UUIDs as primary keys, thoughtful indexing remains just as critical to ensure efficient data retrieval. Equals 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 equals. Final segment, close and summary, 1530 to 1700 hours. Equals 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 equals. So, let's quickly recap what we've learned. Database indexes are not just an optional extra, they are a fundamental component of building performant, scalable applications. They act like a super-efficient GPS for your data, allowing the database to jump directly to the information it needs, rather than searching through every single record. We explored how clustered indexes physically organize your data, making full row retrieval super fast, while non-clustered indexes provide multiple sorted pointers for specific column lookups. We also saw that while indexes are incredible for speeding up reads, they do come with a cost, increased storage and a performance hit on write operations. The key is to strategically apply indexes where they'll have the most impact on your most critical read queries. Understanding how to use and optimize indexes is truly a superpower for any developer. It can transform a struggling application into a high-performance machine, directly impacting user experience and your bottom line. If indexes are the shortcut, what's the teleport for data? Join us next time as we dive deep into the world of database caching and explore how it can make your data even faster, reducing database load and delivering instant results. Don't miss it!